Everybody, my name is Markus and I'm presenting the work on lower bounds for QBFs of bounded Treewidth, which is joint work with Johannes Fichte and Andreas Pfandler. So what is this Treewidth all about? Well, in general, there are lots of problems that are rather hard on arbitrary graphs, but these problems typically become rather simple if we look at the special case of a tree. Well, and the Treewidth now is a way to measure the closeness of a given graph to being a tree, or to capture the tree likeness of a given graph, and the Treewidth itself can be defined in terms of tree decomposition. A tree decomposition of a given graph is an arrangement of the graph into a tree, where each node of the tree, referred to as bag, gets assigned certain vertices of the graph. This has to be done in such a way that the following three properties are satisfied. First of all, every vertex has to occur in at least one bag. In our example here, we see that this is the case for all the vertices of G. Then all the edges have to occur in some bag, meaning that for an edge, the two vertices of the edge have to occur together in at least one bag. Here we see that this is the case for the edge AX, BX, and AB, but we can check that this is true for all the edges of G. Last but not least, we require the connectedness, which basically ensures that if we restrict the tree to a certain vertex of the graph, the result is still connected. In our example, we see that this is the case for C, also for B, and for X, and finally also for vertex A and Y, since both vertices occur only in one bag. So this is indeed a tree decomposition of our given graph G. The width of a tree decomposition corresponds to the largest bag size minus 1, which is 2 in our case, and then finally the tree width of a given graph G is the smallest width among all potential tree decompositions of G. While tree width was originally defined for graphs by Robertson and Seymour in a series of papers, nowadays having bounded tree width K can be seen as one of the most cited combinatorial invariants. In fact, assuming instances of Treewidth K renders a large variety of NP-complete problems tractable. We call this tractability fixed parameter tractability since it depends on fixing the parameter Treewidth K. In such fixed parameter tractable or FPT algorithms for Treewidth, the complexity or the hardness of a given problem is confined to this parameter Treewidth. This allows for a more fine-grained analysis where we get polynomial runtime, but in addition the runtime also depends on the value of a function depending only on the parameter Treewidth K. In classical algorithm analysis, where we do not have this fine-grained tool, we often only consider instance size and cannot confine the hardness of a given instance to some parts. There are also plenty of FPT results for problems believed beyond NP, like deciding the validity of quantified Boolean formulas. One possibility to obtain such results is by using the well-known theorem by Cosell. While this theorem can be seen or can be used as a rather powerful classification tool, it might not serve well in defining the exact runtime depending on K. As an alternative, and to better capture the f of k part of these runtimes, using QSAT was proposed. While this problem QSAT, so deciding the validity of a quantified Boolean formula, is not FPT with respect to Treewidth alone, there are certain FPT results. If, for example, we also consider the quantifier rank of the formula as a parameter, we obtain that the consistency of a QBF can be decided in time L-fold exponential in the Treewidth, while still being polynomial in the instance size. This algorithm goes back to Chen and serves as a first upper bound, but maybe there is some improvement possible. At least for quantifier rank 2, this is not possible if we believe in reasonable assumptions like the exponential time hypothesis. Exactly this lower bound result is, by the way, the reason that makes QSAT so attractive as alternative to Cosell's theorem, because we get precisely double exponential runtime in the Treewidth, which probably under ETH cannot be significantly improved. A similar result was mentioned for odd quantifier ranks by Pan and Vardy in an earlier work. The exponential time hypothesis, or ETH for short, implies that we cannot solve satisfiability of a given formula in better than single exponential time in the number of variables in the worst case. And while this ETH is widely believed, it's actually stronger than P is not equal to NP. So it might be the case that ETH fails, but still P is not equal to NP. This brings me to our contributions. Well, we basically established that under ETH, one cannot significantly improve Chen's algorithm. So QSAT of Treewidth K with quantifier rank L cannot be solved better at runtime, that is L-fold exponential in the Treewidth, while still being polynomial in the instance size. This doesn't only confirm Chen's result, but also more or less agrees that using QBFs or reducing from QSAT might be indeed a nice tool to get exact runtime dependencies on the Treewidth K. The actual proof goes by reduction from QSAT of quantifier rank L and creates a fresh QSAT instance of quantifier rank L plus 1. But wait, if we increase the quantifier rank, what do we get for that? Well, at the same time, we significantly compress Treewidth. More precisely, the Treewidth of the resulting QSAT L plus 1 instance is exponentially smaller than the Treewidth of the QSAT L instance where we started from. This is achieved by guiding the overall reduction along a tree decomposition of the QSAT L instance. Doing so allows, together with the increased quantifier rank, to decouple variables or to decrease structural dependency in the form of Treewidth. We basically evaluate the same formula, but each constructed clause uses at most logarithmically many variables of one bag of the given tree decomposition. Interestingly, we still require redundancy in the form of auxiliary variables, but one needs to take special care to not increase Treewidth in the process. As already pointed out, our result also confirms Chen's result in the sense that it establishes that probably one cannot significantly improve this algorithm. We also complete a methodology on showing lower bounds for Treewidth by using QBFs, and also add a plethora of showcases in the form of new results for existing problems. This now brings me to the core idea of our reduction. Most lower bound reductions for Treewidth we have seen so far start from a given SAT instance of Treewidth K and construct an instance of the desired problem, where the Treewidth is a function in the instance size or the number of variables of the SAT formula. So in this case, to show a lower bound for QZ2, we construct an instance of QZ2 where the Treewidth is logarithmic in the number of variables of the SAT formula. In this sense, our approach is completely different. So we start from a SAT instance of Treewidth K and construct an instance of QZ2 whose Treewidth is logarithmic in K. While both approaches provide a sufficient lower bound for QZ2, the former approach is not so easy to generalize because if we want to go from SAT to QZ3, we require a different idea. Whereas our approach basically allows to use the same idea by induction. So what has been done so far? Well, we have Cosell's theorem in the 90s, and then roughly 10 years later, the ETH was proposed. 5 years later, the result was mentioned for QBFs of odd quantifier rank by Pan and Vardy. Around 2010, lower bounds that are beyond single exponential for Treewidth were established. Around 2015, Andreas and Oliver established that Treewidth alone is not sufficient for fixed parameter tractability of QSAT. In the following years, double and triple exponential lower bounds, as well as the double exponential lower bound for QZ2 were shown. This is then followed by the recent work on suggesting QBF or QSAT as an alternative to Cosell's theorem. Before we go into details of our reduction, we will quickly provide some background on quantified Boolean formulas and QSAT. An instance of QSAT is a so-called quantified Boolean formula, or QBF for short, which consists of a quantified prefix and a matrix. The quantifier prefix of a QBF consists of an alternating sequence of existentially and universally quantified sets of variables, where the matrix is in conjunctive normal form if the last quantifier is existential, otherwise it is in disjunctive normal form. Here we assume that F is closed, meaning that every variable of the formula occurs under exactly one quantifier. And we are interested in the problem QZL, which asks for a given QBF, where we have L alternating quantifiers, whether the QBF is valid or satisfiable. Satisfiability of a given QBF can be easily defined via recursion. So for all xq is satisfiable if for any assignment involving the variables xq under this assignment is satisfiable, and further, exists xq is satisfiable if there is at least one truth assignment involving the variable x such that q under this truth assignment is satisfiable. So quick question, is the given QBFQ of the example below satisfiable? Well, if you take the truth assignment where you assign w and x to 1, no matter how you assign y and z, you will always satisfy at least one term. So if you take the assignment where y is set to 0, you satisfy the first term. If you take the assignment where you set y to 1 and z to 0, you take the third term, and otherwise you take the fourth term. So in any case, no matter how you assign y and z, the formula is satisfiable. The last missing ingredient we need before talking about details of our reduction is so-called dynamic programming on tree decompositions. So how does this work? Well, first we assume a given propositional formula. Then we compute a tree decomposition, but for that we need a graph representation of the formula. Here we use the so-called primal graph, where as vertices we have the variables of the formula, and we have an edge between two vertices whenever the two variables occur together in at least one clause. Similar, this can be done for a formula in disjunctive normal form, where a clause is replaced by term. So assume the given tree decomposition, which you already know, of the primal graph of the given formula. Then dynamic programming on the tree decomposition performs a bottom-up or post-order traversal of the tree and computes for each tree decomposition node a table. Whenever we introduce a new variable that has not been seen in the current subtree during the traversal, we need to guess a truth value for the variable. In the leaf node containing bxa, we need to guess 2 to the 3, so 8 many truth assignments, and then we check the corresponding clauses of the bag, meaning not A or B or X and A or B. This leaves us with 5 rows. This is then continued for the next node, where we take the previous table, project it to B and X, introduce C, and check all the clauses that only use bag variables, which leaves us with the next table. Then we continue the post-order tree traversal and compute tables for the remaining nodes until finally we are at the join node, where we have to merge agreeing assignments. Since the root table is not empty, there has to exist a satisfying assignment, which can be easily reconstructed by following back predecessors of rows. With this technique, we obtain an upper bound for Boolean satisfiability, which runs in time that is single exponential in the Treewidth. And this can be easily extended to QZAT, which is basically what Chen's algorithm does. Okay, wait, but what does this upper bound technique have to do with our reduction and obtaining the lower bound? Well, our reduction is highly influenced by this technique. So coming back to the core idea of our reduction, we start from a formula of Treewidth k, and we compute the tree decomposition whose width is also k, and we guide the evaluation of the formula along this tree decomposition. But then we use an additional quantifier to exponentially decrease the Treewidth of the resulting QZ2 formula. And as already mentioned, this idea of guiding the evaluation of the formula along a given tree decomposition similar to dynamic programming or similar to core ideas of dynamic programming can be easily extended such that we do not start from SAT, but we start from QZI and reduce to QZI plus 1. Next, we are ready to outline our reduction. Maybe as a disclaimer, this is not, so to say, 100% our reduction. This is, as already mentioned, the outline, and I only want to give main ideas and important ingredients of our reduction. This outline highlights the following. On the left-hand side, we see a tree decomposition of the primal graph of the matrix of a given QZL instance. And on the right-hand side, we see a corresponding tree decomposition of the primal graph of the matrix of the resulting QZL plus 1 instance. So we basically see a one-to-one correspondence between a bag of a tree decomposition of the input and a bag of a tree decomposition of the output. And intuitively, in a bag on the right hand side, we want to do the same thing, more or less, as in a bag on the left hand side. It's just that on the right hand side, we're not allowed to have as many bag elements as we have in a corresponding bag on the left hand side. So how do we go from bag size k in the left hand side to bag size log k in the right hand side? Well, in each bag on the right hand side, we are only allowed to address, say, a constant number of vertices in the bag on the left hand side. Technically, this is realized with the concept of pointers similar to programming languages, where with a pointer in a bag on the right hand side, we can address at once any element of the corresponding bag on the left hand side, but only one element at a time. Here pointers are represented via these green P elements. The overall reduction consists of 3 parts called guess, propagate, and check. In the guess part, we guess similarly to dynamic programming algorithms the truth value for introduced variables. However, for each introduce of a variable, we need fresh copy variables given in blue to do that. In the end, it is ensured by the propagate part that these copy variables have the same value by synchronizing pointers using the red squiggly arrows. Let's now have a look at our example QBF as already quickly discussed. In the figure below, we see first the primal graph, then a tree decomposition of the primal graph, and finally a second tree decomposition of the primal graph, which we will use.
Our reduction uses tree decompositions of this form, where each bag has at most one label for checking at most one DNF term.
The quantifier structure of the resulting 3 QBF on Q and the tree decomposition T is as follows. Since the existentially quantified variable W is introduced in nodes T1 and T3, we have WT1 and WT3 existentially quantified. Analogously for variable X. For the universally quantified variable Y, we are only allowed to keep one copy variable under universal quantification, and we have to shift the other copies to the next existential quantifier. Intuitively, in the end, we want to have that the truth values of these copy variables are identical. So the shifted variables have a clear existential dependency on the one copy variable that is universally quantified. Additionally, we add universally quantified pointer bits used for representing a pointer for each tree decomposition node, and we also need existentially quantified pointer values, which give the value of the corresponding pointer target. So how do the formulas for the guess part look like? Well, for W, whenever W is set to 1 in node T1 and the pointer in node T1 points to W, also the pointer value has to be set to 1. Similarly, if setting WT1 to 0, as well as for both cases of WT3. As already quickly mentioned in the outline, the propagate part is responsible for synchronizing pointers. The propagate part for W in node T4 looks as follows. Whenever the value of the pointer in node T4 is set to 1, and in T4 we point to W, as well as in T3 we point to W, then the value for the pointer in T3 also has to be set to 1. Analogously for the case where we set the pointer value of node T4 to 0. The check part is a bit more involved, where we additionally require 3 pointers per bag to check the satisfiability of at least one 3DNF term. The information of the satisfiability is then passed and guided along the tree decomposition, and ultimately in the root node we have to enforce that this is indeed the case. For this check part, we require additional existentially quantified pointer bits as well as pointer values and variables to guide the satisfiability information.
Overall, we obtain this outline, which we have already seen, where values of the introduced variables are guessed in the guess part, and then these values are synchronized via pointers and with the help of the propagate part. The check part is responsible for checking satisfiability of DNF terms, but it is not visualized in this outline.
For formal details and arguments on correctness, we refer to the paper. The paper also contains formal arguments why the resulting QSAT instance has indeed an exponentially smaller Treewidth than the QBF instance where we started. The actual lower bound theorem can then be shown by induction and by applying our reduction, which ultimately goes back to the exponential time hypothesis. By construction of our reduction, the result immediately carries over to the weaker parameter path width, which considers only path decomposition, that is a tree decomposition whose tree is a path. This can even be further generalized to a slightly weaker parameter, thereby providing a stronger lower bound result. With the reduction, we were also able to improve a known result on para-sigma LP hardness, where for details we refer to the paper. This now brings me to the last part of this talk, where we briefly sketch how our reduction simplifies showing lower bounds for Treewidth. First of all, for showing the lower bound for problem P, we need a dedicated graph representation. We decide on a quantifier rank that is sufficient enough, so to say, for showing our lower bound. So for showing an L-fold exponential lower bound in the Treewidth, we require quantifier rank L. Then we establish an FBT reduction from QSAT L to the problem P, where we have to take care that the Treewidth parameter is linearly preserved. Further, the reduction is not allowed to run in time L-fold exponential in the Treewidth, because in this time we could already solve QSAT L. This establishes the same lower bound as QSAT L. So under ETH, we cannot solve P in time that is L-fold exponential in the Treewidth while still being polynomial in the instance size. For details on generalizing this methodology further, we refer to the paper. With the reduction and the methodology, we were able to provide several new lower bounds for problems in artificial intelligence, ranging from reasoning problems over abstract argumentation, as well as logic programming and canonical counting problems. This already brings me to the conclusion. So this work provides new insights on lower bounds for quantified Boolean formulas based on the exponential time hypothesis. Our result confirms that an upper bound that has been known since 2004 cannot be significantly improved under ETH. Core of our work is a new reduction that, while performing quantifier expansion, is able to significantly decrease Treewidth. Our results allow to define a new methodology on using QBFs for showing lower bounds for Treewidth, and we provide plenty of showcases. For future work, one might continue showing lower bounds of existing upper bounds, or think about generalizing the methodology to further cases. It might be also interesting to consider extensions of the ETH, like the strong exponential time hypothesis, and to see how our reduction performs in practice. Thanks for your attention.